Hello, everyone. We are here with Elaine Weyuker, and she is going to give her keynote, the view from 40 years in the research trenches, from academia to industry and back again. Elaine is a self-educated programmer, later system engineer. She joined the New York University and stood there for 18 years as professor, and then moved to ATT and spent almost another 20 years there. Now she's back in the university. It's an unusual career, and she's going to tell us more about that. Elaine, the floor is yours.
Thank you. So I'm going to try to talk about 40 plus years in less than 40 minutes. I started as an academic, uh, continued as an academic with doing industrial consulting, then moved to industrial research, and now I'm back again, as Oscar said, as a researcher. But first, I have to start at the beginning in the mid-1960s when I was still in college as a math major. At the time, there were no computer science majors available. Most colleges, including my own, offered no computing courses at all, and there were no computers on campus. So I made two important decisions as during the first semester of my last year in college. The first was to apply to a PhD program in computer science at the University of Pennsylvania within the School of Electrical Engineering, even though I knew nothing about either computing or engineering. And the second decision was to graduate from college a semester early and get a job as a programmer. I got a number of offers. I took an offer from Texaco, which was then the fifth largest company in the US, and in many ways, a leading technology company. So off I went to Texaco, and since I didn't know anything about being a programmer, they gave me a self-instruction manual and told me to read it. And after 2 weeks, I thought I had mastered everything about programming the IBM 1401, 1410 series. And so I was given a test. And since I passed with flying colors, I was now a full-fledged programmer. And they gave me my first assignment. And that was to automate their credit card application. And basically, that's what almost all programming was in the mid and late 60s and well into the 70s. It was automating existing manual processes. And the perspective was that the reason you wanted to automate everything was it was more efficient and faster. And more to the point, it was less error prone. Humans make mistakes, computers didn't. But what people, by and large, didn't recognize was since human beings were writing these programs and human beings made mistakes, there were going to be bugs in the software. But that was not the central or universally recognized. So I wrote my first program and key punched it. And then they told me I should desk check it. And what desk checking meant was you think up some scenarios and you hand simulate them. And they gave me no guidelines for what type of scenarios to choose or how much desk checking to do or when I would be done desk checking. They just said, go desk check. So the reason that they emphasized that desk checking was important was that the computer was rightly viewed as a very scarce, very expensive resource. My time was cheap, the computer's time was expensive. And there were two perspectives on why it was expensive. The first was Computers cost a lot of money. They had very few. By today's perspective, they were very slow, um, and very small. And so we were using the very same programs that were running the company's workload, the already automated jobs, um, to run our development jobs. So you did not want to waste spare cycles. You did not want to do a lot of testing on the machines because it was wasting time that could be used and needed to be used for the company's mission. The second thing was you got 3-day turnaround. And let me explain what this meant. When I finished checking the job, I put my job along with everybody else's into a box. And once a day, a van came over and picked up all the jobs to be run and drove them over to the computer center. The computer center was in the company headquarters with the executives because computers were important. The programmers were literally in a warehouse somewhere else. So, and then it would be run in the computer center sometime when there were spare cycles. And 3 days later, when the van came to pick up that day's um, submissions, it would bring back my output. And then I would look at the output and see, did I make any mistakes? If I made the mistake, I had to find the bug, fix the bug, redesk check, resubmit, wait another 3 days. So every time I had a mistake that was found by running uh, my test cases, meant I was wasting another 4, 5, 6, 7 days. And so that was bad. And so the emphasis was desk check carefully so you're not wasting the computer's time. What I can say is that the very first program I ever wrote, this credit card application, ran on its first run, ran correctly, and was released to the field. And in the almost year that I worked as a programmer at Texaco, I wrote a lot of programs, some of them very, very sophisticated based on my mathematics background, such as automating and developing optimal tanker routes because I had an operations research background as well as mathematics. And they were all released and were running, and you knew if you had a problem while they were released to the field because you had to put your home phone number on every program that was released. And they would call you in the middle of the night and tell you, get your clothes on, get on the subway, come on in and fix your code. And since I never got one of those dread codes during the night, I guess I was pretty good at programming. I know I was not good at testing. In any case, I then went off to Penn to be a graduate student. While I was at Penn, I took a whole bunch of different courses in all kinds of areas of computing, compilers, programming languages, advanced programming, system programming, microcoding. I can safely say that in all the courses I took at Penn, I never once heard the word testing uttered. After 2 years, I decided I had enough of being in an engineering school, so I wrote a master's thesis in, surprisingly, AI, natural language processing, got my master's degree, and accepted a position at IBM as a systems engineer. The first thing that happened as a systems engineer at IBM, even though I was really one of the most experienced people they had hired, this was the late 1960s, I had industrial programming experience, and I had a very rare master's degree in computer science. They sent me for a 3-week intensive training course in the IBM 360 series of machines, which was then absolute cutting edge technology. And frankly, IBM was without a doubt the preeminent tech company of the day. Um, at this 3 week intensive course, which you had to take away from your home because you took classes from 9 to 5, and then every evening you had these assignments to do. We learned system programming, details of the operating system, all kinds of programming languages, details of how disk operating system worked. I did not hear one word about testing. I came back from the course and was assigned as a full-time um, systems engineer to the team at Penn. At the time, IBM, for their best customers, uh, provided full-time system engineering on-site um, support. Penn was the Philadelphia office's largest customer, and so we had a team of 6 systems engineers full-time at Penn to do whatever Penn needed. There were 4 software systems engineers, including me, and 2 hardware systems engineers. I wrote a lot of system code. I guess I was okay at doing it. I guess I tested okay. They ran, they were used. Um, I don't know. And then after a little more than a year, I'd had enough of doing that and took a position at the City University of New York as a full-time teaching faculty at an interesting college, which had only juniors and seniors. Our students were coming in from local community colleges. I was their first CS faculty and the only CS faculty. I stayed there for 6 years. I taught 6 courses a year, mostly upper division courses, basically everything you could think of in computer science, compilers, operating systems, advanced programming, system coding, etc. I also taught beginning programming for non-computer science majors, mostly for other STEM fields. I used all the standard text. I can safely say that none of them mentioned testing, so I didn't mention testing. And my students were not going on to graduate school. These were students who wanted to get good paying programming jobs. I was training the next crop of industrial programmers. They typically finished with me. Everything they knew about programming came from me. Um, and they usually got very good jobs in local New York City industry, utility companies, banks, insurance companies, sometimes local government. After 6 years there, it was now the mid-70s. I decided it was time to go back and finish my PhD and become an industrial researcher, which was become an academic researcher, which is what I had originally planned to do. So off I went to Rutgers, um, and I entered in September 1975. I spent 18 months at Rutgers. During that time, I took 30 credits of courses. None of them said anything about testing. I wrote my dissertation in a very theoretical area of theory of computation. I had my defense 18 months after I entered in March 1977. I got an offer from NYU as a tenure track assistant professor. And I had 6 months between when I had my defense in March 77 and September 77, when I would be going to NYU as a professor. And so I decided I would pick a new research area because I really did not want to continue doing theory of computation, although I later wrote a book in it. And I decided, for a variety of reasons, to choose software testing. At that time, software testing was a minuscule, nascent research area. The reason I chose it was that I had spent 11 years working at two cutting edge, very large corporations. I had been at two different graduate schools. I had trained the next set of uh, programming professionals, and nobody was talking about testing. And I felt it was really important. I felt like I could really make an impact, really make a difference in the way, in the quality of software that was developed. I was getting increasingly concerned about the quality of software, and as um, as the ubiquitousness of computing was becoming much more apparent. The other thing was I thought it'd be really interesting, but primarily I thought I could make a difference, and having had this pragmatic experience would help me um, sort of bridge the gap between researchers and practitioners. So I went to NYU. In 1978, I wrote my first testing paper. It was joint with Tom Ostrand, who was then at Rutgers. And it was at what I believe was the first software testing conference. If not, it was one of the very first. It was a workshop that later became what we now know as ISTA. I can say that at that workshop and for at least the following decade, all through the 80s and well into the 90s, there were two main categories of papers. There was a very small community of people who were doing theory of testing. And initially, that's what Tom and I were doing. We proved things about testing and identified characteristics of testing strategies. But the overwhelming majority of papers that were being published in the software testing community were methodological. It was, here's a new way to test software. And if they gave any evidence at all, it was basically giving a plausible explanation why this was a smart way of doing things, and showing some tiny toy program, sometimes with a couple of seeded errors, so the person could see how, so the reader could see how this newly proposed technique would work and how they would find these seeded errors. What's interesting to me in retrospect was that if you read the old research literature all through the 80s and early 90s, the research literature said the state of the practice used statement and branch testing. And I knew that wasn't true. I knew that I had worked in the industry and nobody there was talking about statement and branch testing. But much more to the point, once I started at NYU, I started doing a lot of industrial consulting. We were allowed to. And I felt that that was a way of supplementing my pathetic income, but also giving me insights to what the real problems that practitioners were facing. And I could say that through the 70s and 80s and early 90s, I did not encounter a single company that was using statement or branch testing. In 1982, I had my first ICSI paper. It was introducing the Dataflow family of testing. This is a figure from the original paper. I can say that that paper, almost 40 years ago, along with the associated TSE journal paper, is without a doubt my most widely cited paper. And to this day, there is not a week that goes by in which I don't get new citations in that paper. So in some ways, I'm very proud of the fact that my first ICSI paper 40 years later is still being widely cited. It I think the big contribution, although I do think that this is a sensible way of testing programs, and I was doing a lot of consulting then, and a lot of companies were real interested in hearing about it, but I firmly believe that none of them actually really used it in practice. I think the big contribution was that I provided a concrete way, which I think was unique, of saying this testing strategy is better than that testing strategy, in the sense that any strategy that appeared higher up in the hierarchy, in this lattice, was guaranteed to do a better job than ones lower down the strategy. So, for example, um, if you use the all uses strategies, you were guaranteed that you could find any bug that branch testing or statement testing would find. On the other hand, you would find bugs that would be missed by the typical statement or branch coverage test suite. And in addition, I did complexity analysis, a cost benefit analysis. I said, well, it's true that all uses is a better way of testing from the point of view of fault detection. On the other hand, or assessing the comprehensiveness, using this as an adequacy criteria, and assessing the comprehensiveness of testing. On the other hand, it costs you. And I could say in a concrete way that yes, you'll find more bugs, but it will cost you this much more than doing these less demanding strategies like like statement and branch testing. I think that was an important contribution. In 1984, Tom Osran was at Univac, which was then a major computer manufacturer, and I was consulting for them. And because he was working full-time for them, he was involved with this production software project, and we got access to do an empirical study with using their bug data. We were very, very heavily influenced by Vic Basili and Marv Zelkowitz, who were then partnering with Frank McGarry at NASA. And they were definitely the grandfathers of empirical software engineering and were championing why empiricism was really important. And we learned an enormous amount from our interactions with them. They were interested in improving the general software process, and their empirical studies focused on process improvement. We did what I believe was the first industrial study in software testing per se. In any case, it was an early one. It was doing bug categorization. We developed a taxonomy. That's also still somewhat widely cited. It was a very lonely time to do empiricism. Although Basili and Zelkowitz were really doing, and we were trying to do Lantman work, explaining why this was impossible. There was very little buy-in, certainly in terms of doing industrial studies. And in a sense, it was understandable. It was very, very difficult to find an industrial partner who was willing to let you look at their bug data. And that's true for today as well. And the other thing was, for an academic researcher, and I was at that time still an academic researcher, it was a gamble. You know, you're worried about getting tenure, you're worried about getting promoted, and doing empirical studies is much slower than writing a non-empirical piece. It takes time to collect data, it takes time to clean data, it takes time to do everything. And um, and if you're worried about getting a lot of publications out the door, doing empirical studies was not viewed as the route to success. Nonetheless, I still felt it was really important, and really the way it made my research um, interesting and potentially impactful, which again was what my goal was. In the middle 90s, um, I moved to AT&T Bell Labs, and there's a backstory here. The labs was one of the places I was consulting. I was consulting for a large number of corporations at that time. Mid 90s, the labs had been trying to convince me to move there full time. What they finally came up with was they had a Nobel Prize winner call me and try to convince me to move. And at the time, I was a tenured full professor at NYU. Um, I was successful. I really was happy there. But he convinced me to try working full time at the labs. And what he said to me was, look, we have 450 million lines of code that run 24/7. And if you move here, you will have total access to anything you want. And he convinced me to take a 2-year unpaid leave from NYU. So if I wound up not liking the labs, I could always go back to NYU. And so off I went to the labs um, to try it. Um, and what I can say is I wound up staying for just under 20 years. Um, from the day I walked in the door, there was somebody who was head of technology transfer. I was in the research division, but he was thrilled to have somebody who wanted to work for work with production software projects. He helped me make connections. My first partner was Alberto Evritzer, who was in the was working as a practitioner. He was doing load testing and performance testing. We developed a whole bunch of strategies which were used on the projects he was working on. Every paper we wrote together had a good industrial case study with systems running 24/7 that were hundreds of thousands of lines of code. Um, we learned an awful lot. We did things with performance review, with architecture review, with various kinds of testing strategies. I then partnered with a number of other people um, doing other kinds of things. Eventually, Tom Ostrand moved to the labs and we started doing software fault prediction models, always with working projects. So in the 20 years I was there, I wrote many research papers. Every single one of them included an industrial case study to assess the effectiveness of what we were doing. And now, at the time that I moved to the labs, Vic Basili did another very important thing. He started the Journal of Empirical Software Engineering. He was the founding editor-in-chief. I was one of the founding editors. The goal in the mid-90s of the Empirical Software Engineering Journal was to emphasize the importance of empirical assessment. As I said, it was a very lonely time to be an empiricist, and to give those people who were doing empirical studies a place to publish. And I think that was a very important contribution. The journal has flourished for 25 years. In 2011, 10 years ago, I gave the keynote address at the Empirical Software Engineering Conference. And for that keynote, I surveyed every single software testing paper that was published in either a major testing conference or a major software engineering conference or journal. And what I found 10 years ago in 2011 was that the majority of software testing papers still contain no real empirical studies. And if they had any empirical evidence at all backing up whatever they were championing, what they were done with student-written programs using students as programmers, or they were using the so-called Siemens suite. And the Siemens suite sounds like it was a suite of 7 or 8 programs written at Siemens Corporation, but in fact, it was not. It was a set of toy programs written by Tom Osrand, who was then at Siemens, along with one of my former PhD students, Tara Garadia, and a couple of other colleagues. And they wrote these toy programs that were a few hundred lines of code in order to experiment with. And one of the things they did was offer to freely distribute them so other people could experiment with them. And they got known as the Siemens suite and were very widely used to do empirical studies. But these were still toy programs. The one ray of sunshine from my point of view in my 2011 survey was there was a growing group, but still a small number of groups of researchers, top flight researchers, academic researchers who were using open source softwares that were increasingly becoming available, things like Eclipse, Apache, and they were taking advantage of these systems to do studies. I think that both using open source software and industrial software are both very important. I don't think they're the same. Although open source software is widely used, and so from that point of view is real, they don't typically have the same kinds of issues that industrial systems have. The industrial systems, your entire corporate fortunes are running on them. You have critical deadlines. You have people who are full-time doing nothing but testing, nothing but development, with incredible deadlines. Open source don't have the same kinds of pressures on them for the most part. And so, although I think using them for empirical studies is extremely valuable, I don't think that it's a substitute for understanding what practitioners' real needs are and what they are actually doing in the practice. When I was preparing this talk, So in 2012, I left AT&T, and I took a position at Mälardalen University in Sweden. I continued to live in New Jersey, and I went periodically to Sweden, and that's a university that has very strong collaborations with a number of international research companies, and through them and companies I was still having consulting relationships with, I continued to interact with the people in the trenches. So last month, when I was preparing this talk, I contacted a number of professional testers at roughly a dozen of these international corporations that I've been interacting with, and asked them two important questions. The first is, to what extent are you doing initial test suite development, or how are you doing initial test suite development? And 100% the answer is test cases, test suites are still developed manually at every one of these companies based on a natural language specification or documentation of some type. And the second question I asked was, how many of you are using some kind of coverage criteria, particularly statement and branch coverage, and not a single one of them was using it. And I can say that in my 20 years at the labs, I never came across a project that uniformly used statement or branch coverage, even though we frequently championed it to them. Which was kind of disappointing. I did find that some of the companies, and in fact, some of the companies that I had partnered with, and some of the papers that I've published very recently as in 2020 ISTA, were automating regression testing, but not initial test case production. I was very, very excited when I saw the 2019 FSE paper written by some people at Google, which said they were using, they had created a line coverage tool, which was in the, which was open to all production projects. They were championing it. It was increasingly being used. Line coverage was essentially statement coverage, but it was not universally being used, but at least people were using it. And how exciting, something from research has made its way into practice at one company. But on the other hand, how sad it is that it's technology that was introduced in the research community more than 50 years ago. And so when I look in retrospect, I still see this enormous gap. I see we, the researchers, standing on one side. I think the research community is doing some really interesting things. And I see the practitioner community having to test software that are multi-millions of lines of code, which enormous performance and reliability and security requirements, and needing real help. I think the problem is that too many researchers do not really understand the scale and the scope of the issues that practitioners face because too many academic researchers have never themselves um, actually engineered real software systems or tested real software systems and stood in the trenches. And they are not, and practitioners um, are not really seeing things that they feel that they can use in their daily lives. And we have to come up with better ways of bridging this enormous gap. And with that, I'm open to questions.
Thank you, Elaine. Awesome talk. I really enjoyed it. It was touching. Dear, we are here for a short Q&A. Awesome talk. So please, if you have any question or consideration, please go ahead and use the chat. And remember that after the Q&A, we all will have the chance to meet Elaine in a breakout room where we can talk this time reality with our own voice instead of writing in the chat. So we have the first. Prefer to read it yourself or?
No, why don't you pick questions and
Okay. I will start with in sequence. It seems to me that the problem is that the focus on testing software against specifications in industry. Most of my time, specifications are completely informal and therefore do not facilitate the fancy testing methods that come from researchers. So the guy that makes the specifications are the culprit. That is interesting.
no, I don't think that's I think that Michael is absolutely right on. And that's a problem that um that many practitioners say, you can tell me that I can start with my formal specification, but I don't have a formal specification. What I have is 40 pages of text, and that's what I get to test against. And you're absolutely right. There, the technology in industry in terms of specification has not changed, but the assumptions that we in the research community are making frequently are not based on those realities. And that's why this gap continues.
Justus ask, what is your opinion about the current state of empirical evidence for the new metrics that some tools as SonarCube are using?
I'm not sure.
That's good.
I don't know, because I don't know people who are widely using them, so I don't have an opinion about how one of the things I'm never embarrassed to say I don't know, because I don't really have firsthand experience with that. What I can say with people, with the projects that I still interact with on a regular basis, and they're not using these things.
Mhm. We have a question by Gerardo, and says, do you think that the test, at least the initial test cases, could be automated?
Do I think
Automatically generated. I understand that's the.
do I think they could be all? Yeah. So there's lots of stuff about automatically generating test suite. So what are you going to automatically generate them from? You could do random testing, and that's something you can do. I'm not a big fan of random testing. Um, uh, the chance of, I mean, I do a lot of statistics. I understand statistics very well. The place, in a very large input space, the chance of hitting the places.
Excuse me a second, Elaine. We're running out of time in the live stream, but we can move now to the discussion room. You will see the pop-up. Everyone that wants to join us in the discussion room, please press the button. We will meet